I did some digging online and I found the PowerShoot software that works with this model of UPS. It was a little bit difficult to find because this is a really old unit and the current software doesn't work with it, but I did find that on their FTP site, which is kind of hidden. With the UPS I got a bag of crap that actually came with software that isn't compatible with my UPS, so that didn't do me much good, but it did come with the APC custom cable. It looks like a standard serial cable, but it's not. If you try to use a standard cable, it will not work. You need to use theirs. But in their software, it's kind of nice. It tells you voltages, battery capacity, all kinds of other things, including an alarm test, which is exactly the opposite of what I want. But it does have this shutdown parameters menu, and you can change various things in here, but the main one is this audible warning. I changed it from power fail to at low battery. So now it will only beep once the battery is low, and then it'll run for an additional 10 minutes until the battery is either fully depleted or you do something about it by turning it off or switching batteries. Hit OK, close the software, and the UPS will now remember those settings indefinitely until I change them again. Now that I have the beeper silenced, I can move on to testing the capabilities of my new UPS without going completely insane. So I took the cover off here, and I'd mentioned before that these transistors I suspect are going to overheat. There's 4 of them in there. You can only see 2 from this angle. But they have a large thermal mass, a block of metal on each one, but no real heat sinking. So I think those are probably going to get warm. We'll see what happens there. The other item that I'm somewhat concerned about is this transformer down here. It's, I don't know. We'll see. I'm not sure which one is going to get hot first, but that's why we're going to load test this to find out. As a load, I have a standard dual light halogen work light here that I'm just going to plug into the back of it and use that as my load. It has 2 lamps on it. Each one is about 250 watts, and there's a low and a high setting on each one. So I can turn one on high and the other one on medium, and then I can get just about a full load on this because it was originally rated for 400 watts or 650 volt amps by the American Power Conversion Company. So to measure the temperature of these transistors here under load, I need a way to measure that temperature, and I do have an infrared thermometer that I can use to measure temperatures with. It's set on Celsius right now. Must be about 22 Celsius in this room. But I can't use that to measure the metal heat sinks here because they're metal. And metal has a low and unpredictable emissivity, so I can't use an infrared thermometer on that. What I'm going to use instead is this thermocouple meter here. It has a thermocouple on the end, and it'll report temperature by contact. So to measure that temperature, all I need to do is stick this on the transistor, and I should be good to go. For the transformer down here, it's a little bit different problem. It's a pretty standard construction transformer for consumer electronics. It's copper wire wound around a laminated silicon steel core. It's laminated to reduce eddy currents. That helps it operate like a transformer instead of an induction cooker. And they use silicon steel instead of soft iron for a similar reason. It has a higher resistivity. In any case, why is that important? It's important because I just mentioned that I can't measure this because it's metal. The transformer is clearly metal. Yet I plan on using this infrared thermometer on it. One simple way around that would be to measure the temperature of the non-metal part. But this is some sort of resin impregnated paper product, and really it's an insulation blanket. I don't care what temperature that is, I want to know what the temperature is inside. So I really need to measure this metal core. But fortunately it is black anodized, so it has a heavy oxide layer on it. They do that to insulate the laminations. And it's also coated with some sort of lacquer product. I don't know what it is, but it does actually record report the correct temperature with my infrared thermometer, so I can just use that on that one. So I'll take the thermocouple, and I'm just going to put this on here, just tape it on. That'll be good enough for this test. If I can get it on here. There we go. Set this here so you can see it. And I'll take my deluxe thermometer stand here, just aim it in the general direction of this transformer. It's pointed at the outside of that anodized metal now. And I'll just put this rubber band around it to lock it on. There we go. So I have the temperature of those transistors and of the transformer reporting on here. I think you can read them both. So then I have my load back here, and I'll turn the unit on. Once again, I'm not sure why it was unhappy there, but it is on and running now. So I'll turn the load on. Dim, bright, and dim on the second light. So now I have about 400 watts going there on those lights. And we'll just do a time lapse here and see what the temperature does over time. Alright, it's only been running for a few minutes, and you can see that the transformer really hasn't done anything, but the transistors here, they're getting way too hot. I'm going to turn the load off here. Alright, the load is off, and those transistors are 75 Celsius. They're about ready to start on fire pretty soon. So clearly the transistors are what I have to worry about. The transformer is probably making some heat, but if I let it run for an hour or two, it might get pretty warm. Right now it's still cool to the touch. So the transistors are what I have to worry about. I'll see what I can do about those. I have the control board completely out of the UPS now. It's very difficult to work on it in the unit, so I just disconnected it entirely this time. A little better close-up of it. Here's the front with all the components. And if I flip it over, the back is pretty plain. It's just a single-sided PCB assembly, low-cost assembly like you'd expect in consumer electronics. And I looked at this a little bit closer to try to figure out what I could do to keep these transistors from overheating. And I realized that I was incorrect earlier when I said that these four constituted an H-bridge. It's actually a lot simpler than that. They connect the center tap of the low voltage windings of the transformer to battery power, and these just alternately pull either end of that low voltage winding to ground, making the alternating current. So really there's just two transistors on here, one bank and the other bank, and then they have two in parallel. So my options for making these cooler are some sort of forced air system, or I could make new heat sinks that are larger. These are already pretty big, they just don't have a lot of surface area. I could replace the transistors, potentially, but I found that there's another option here. You can see that there's two on this side of the heat sink, two on this side, and in the center there's a location for four more. And when I inspected the circuit board, I see that these are just in parallel with the other ones. So all I have to do is drop more transistors in there, and it should be a little bit more efficient. I can't really see what the part number of these transistors are, because the heatsink covers up the writing. All I can tell is that they're made by International Rectifier, which doesn't really tell me anything at all. But I can tell just from how they're used pretty much what they are. And I actually have this bag of transistors from Infineon, it happens to be. These are very high quality transistors, probably cost a few dollars each. And they're going to be way better than what's in here right now. So I think what I can do is, without really desoldering anything, I can probably bend these heatsink tabs out a little bit and just slip the transistor straight in into the PCB. And I think I can just add those transistors right on here fairly easily. At least I'm going to try. So to do that, I have my soldering station here. I'd highly recommend anybody that does soldering on a printed circuit board to get a real solder station. Otherwise you'll end up with cold solder joints or a delaminated printed circuit board. Either way you'll end up frustrated. So I'm going to give this a try, see what happens. Alright, and there we have it. The board now has 4 additional transistors, and each one of these is probably 4 times as good as the one that was in there. So I'm hoping that this board doesn't get nearly as hot anymore. We'll do the exact same load test again here and see what happens. I'm also going to note that the transistors that I used are 30 volt transistors, which is really marginal for a 12 volt system. But that's what I had on hand, so that's what I used. Hopefully they hold up. I added those 4 transistors, as you just saw, and I'm running another load test that's pretty much identical to the last one that was just shown. The only real difference is I connected the thermocouple to this bank of transistors, because those get hotter because of where they're placed. So this is more worst case than the last one, but in any case, you can see that the temperature is much lower than it was last time. We were up at 75 degrees Celsius before, now it's at 40. So these are doing a much better job than the old transistors. I had mentioned that 30 volt parts on a 12 volt unit like this is quite marginal, and unfortunately that was true, because when I powered it up they exploded rather spectacularly, followed by me frantically running around opening windows to get the smoke out. But what I did when that happened is I dug through my stash and found some appropriate transistors. These are 60 volt parts, and went through and spent 45 minutes replacing all 8 of them with these. That's what I get for being lazy and using the first ones that I find, I guess, instead of actually grabbing the correct ones. but it's working again at least, and seems to be working pretty well. The temperature kind of slowed down and isn't climbing much more. So this is about a 400 watt load, and now that the transistors are upgraded, the control logic doesn't know that, and it's still going to limit this to about 400 watts. So if I go back here and turn both lights on bright, that'll be about 500 watts, and you'll notice that the overload indicator turns on and the unit's going to shut down. Turn that off. So the beeper's still on here. It still warns me of an overload condition or a critically low battery. I didn't want to disable it entirely by just desoldering it, so that's why it's still on here. But the next thing I want to do is increase the current limit on this so that I can run a larger load. And I'll show you how I'm going to do that next. Here's the top of the UPS again. And remember that current sense transformer that I had mentioned earlier? That is located right down here underneath, behind that connection there. And if I come back up on top, this side is the AC side of it, these two terminals here. Your AC current flows through that, and on this side is the low voltage side of the transformer. So this will detect how much current is flowing between these two leads. So what I'm going to do is just jumper across these with a piece of wire. Then the amount of current is going to be divided between the transformer and the wire across here, and it should see a lower load than what's really going through it. And that'll allow me to increase the current limit of this. I'm not sure exactly what gauge wire to use, so I'm just going to grab something random, stick it on there, and load test it and see how that works. I put the jumper wire on there as I described, and did some more load testing, and found that it can now supply about 700 watts, after which the transformer inside limits it. And there's really nothing I can do about the transformer except replace it, so 700 watts is where I'm going to have to stop. It used to be a 400 watt unit. But there is one thing left that I want to do with this. It's in a closed box. There's no ventilation except for a little bit of grating on both sides. And it will overheat if it runs too long. So I'd like to add some ventilation to this. I have a fan here that I took out of a piece of old equipment. It's a 12 volt fan and a fan guard. And I'd like to put this about here on it. Then it can blow air inside and come out the two ventilation holes that are already existing. But my main problem is cutting a round hole for a fan. I don't know exactly how to do that without buying a special bit just for this, and I'm not going to do that. So I'm going to give my aviation shears a try. This is fairly heavy gauge metal, and I'm not sure how it's going to go, but when I come back we'll either have a round hole or a really ugly, jagged, sharp one. I'll find out. I'm back with my APC cover that now has a fan in it. I first scribed a circle into it and then drilled a hole and used my aviation shears to cut out a mostly round circle. It turned out pretty good that way. I was somewhat surprised. Then drilled the 4 holes and mounted the fan in it. So that part's done, and now the question is, what do I do with these? I could hook them directly up to battery voltage, but then anytime it's connected to a battery, whether it's on or off, it'll continually drain the battery until it's dead. So if possible, I'd rather hook it up to something that's only live when the inverter is running or only live when it's plugged into the wall. And I only found one location on here that is like that, the battery charging circuit. Unfortunately that's AC, not DC, so this is a DC fan, 12 volts DC. So what I'm going to do is make a very simple rectifier with a single diode and a single capacitor, and that should allow this fan to run off of that power. And then it will, I can turn off the unit when it's hooked up to a battery and the fan will stop, just like it should. What was once a 400 watt UPS is now a 700 watt UPS / inverter / power conditioner / battery maintainer. It took a fair amount of work to get it to this state, so was all the work worth it? Well, it depends. If the point here was just to have an inverter, I would have been better off just buying one. But on the other hand, it did only cost me about $10, so from a strictly financial point of view, yeah, I guess it was a success. But for me, the real point is not the money or the time. It's taking something that was being thrown out and turning it into something useful again. A battery that was being thrown away, an inverter that was being thrown away, a fan that was being thrown away. So a little bit of work, and now I have something useful again. But in any case, this was my UPS to inverter project, and hope you enjoyed watching.